Okay, so today I'm presenting Euler Method, which is a very simple method that allows you to approximate the solution of ordinary differential equation. Okay, so well, what's Euler Method about? Let me firstly illustrate the method graphically. Euler Method is a method that allows you basically to approximate a solution to a differential equation. So what's solution to differential equation? Well, assume that we have a system of coordinates, say system like this. This is y-axis, this is x-axis, and assume that we have a function running like, say, this. Okay, this is our function f of x, and what's Euler method about is that we set several points. Say this one is x0 is the initial point. It's right here, and we approximate this curve by its derivative. Okay, so that means that at the first point we approximate it like this, say like this, because here we know what's the slope of this curve. Okay, so we approximate the solution by this straight line, and here again, here we are, say here we are, say at x1, and here is our y1, and so at this point we again check what's the slope of the derivative. So we check for the slope right here, and we create a curve running from this point. Okay, so let's say the slope right here is like this, and so we approximate the solution by a straight line running like this. Okay, should be like this, and we get to x2 and some y2. Okay, we are at this point, and so here again we again check for the derivative, which is a slope right here, and it tells us that we should draw a line like that. Okay, because the slope is like this, the slope is like this, and so we shall draw a line with the slope. Okay, and so on and so on, and as you can see, we are somehow approximating the exact solution. Okay, we are approximating the fx function, and that's the basic idea behind Euler method. Okay, so use derivatives to obtain the slope and approximate the solution by a straight line. Okay, so let me put these ideas into equations. So we basically have some relationship which we define as dy with respect to dx, which is a function of both of these variables x and y. So what we are going to get is that we have a differential equation, ordinary differential equation in this form. Okay, so this is our initial point to create the algorithm. So put any differential equation to this form, so that you have dy with respect to dx is a function of x and y. Afterwards, choose some n, say n is 5, and this will be the amount of points that we will use to approximate the solution, okay? And if we choose this number, we immediately have that x0 is some x, x1 is x0 plus h, x2 is x1 plus h, etc., etc. Okay, and this will define our x-axis. Okay, this will discretize the x-axis into equally distant points. Okay, and between every points, between every pair of points, there is a distance of h. Okay, and when we have this set up, we approximate the solution of the ordinary differential equation in the following way. We have y I plus 1 is equal to y of I plus h times ki, where ki is basically this at x I y I. Okay, so this is the output, the approximating output. Okay, so just to give you a simple example, let's say we have say ordinary differential equation that drives the money market account. Imagine that as a current account with continuous compounding. So such a differential equation is described by the following ODE. dBT is equal to R BT dt. Okay, and what this differential equation actually tells us, it tells us that the dynamics of the money market account is driven by the following principle. We have some amount b of t, and in every small time step dt, it earns risk-free rate multiplied by the current balance. Okay, and this is the increment of the balance at that moment, and this way it passes through time. Okay, so there are infinitely many time steps, and this is the way how the interest grows on the money market account. Okay, so we are going to put this into the form we have defined right here, and we have dB of t with respect to dt is equal to R times b of t. Okay, so this is exactly the same what we have here. Okay, R is just some constant representing interest rate, which we assume that doesn't change. We assume it doesn't change throughout the saving period. Okay, and so we assume there are some n steps. We set age is equal to sorry, let me illustrate firstly the problem. We are going to check what's the balance of this money market account after, say, 5 years. Okay, so assume that the interest rate is 5% and that the saving period is 5 years, and that the current balance, the balance times 0, is, say, $100. Okay, so these are the this is the initial condition, and this is the this is the account setup. Okay, and so we are interested what's on the account after 5 years, and we would like to approximate it by, say, 10 steps. So what it will look like is that we firstly define t0 is 0, t1 is 0 plus age. But what's age? Age is t divided by the amount of steps, and that's 0.5. So this will be 0.5, t2 will be 1, etc., etc. Okay, and then we just simply use this equation just with the variables for the money market account, so that we will have bi plus 1 is equal to bi times age times, and what's our ki? This is RBT, okay, because it's represented by this, so it will be RBT I. Okay, let me put it into these brackets so that you know that this belongs to ki, and h is just simply the h from here. Okay, and this is our approximating relation, and this relation this mechanism we will implement in C++. Okay, so let me start with a new project. Okay, some console application, hit next, console, empty project, finish, add a new file, let's call it main, and we have just empty file. So we start typically by writing integer main return 0. This is the necessary part that will always be present, and we will define a function. We will define a function returning double, and the function will be called Euler Method ODE. Okay, and we have to enter some parameters. Well, what I will use is a function pointer. Okay, I will be passing a pointer to a function. So we'll be passing some pointer to function that returns double. Say the function pointer will be called pfun, and it takes 2 arguments. Okay, so the first argument will be double r, and the second argument will be double what's it called, let's say bt. Okay, and there are a couple more things entering this function. There is an integer with number of steps. Then we need the initial point, so double initial b, and the capital T representing the final time of the saving period. Okay, and to make this work, we also need the ODE, double money market ODE, that returns bt times r. I think, yeah, this actually here represents the function of this. Okay, because this is the ODE, so we plug in r and bt, and it will return the left hand side of this. Okay, it will return the derivative, so it just takes bt and r and returns this simple number, bt times r, or rbt, doesn't matter. Okay, and the Euler method ODE will refer to this ODE. So we start here by setting up the age. This is the shift on the x-axis. Okay, so double age is equal to, and here we recast the result, t divided by n steps. We are recasting because we are dividing t by integer, and we would like the result to be double. Okay, we'll also use a vector, so let me just write here that we are including vector and using namespace std. Okay, so here we can use the vector class, and let's call the vector that will hold the output bt. Okay, so the first thing we plug into the vector is the initial value of the money market account, which is the initial b, and then we construct a simple loop for integer I is equal to 1, when I is less or equal to n steps, iterate I++. Okay, so we have constructed a very simple loop, and within this simple loop we always calculate the the slope of the derivative, which is double ki is equal to, and this is the result of the function that is referred to by the pointer, so p fun or pt I also need double R like this. Okay, and bt of the previous step. Okay, and now we can go further. We can finalize this. So the bt will hold the value of bti minus 1 plus h times ki. Okay, so this is exactly what we have here. Okay, so we sum the previous value of the money market account and we add something more to that account, and this function has to return some value, so it will return the last element of bt, which is bt, where the index is bt size minus 1. Okay, so let me test this algorithm. Firstly, we have to define a function, the pointer to a function that will be passed to the Euler Method ODE algorithm. So we have to define double p fun that takes 2 arguments of double is equal to the address of the function money market account ODE. Okay, so we are somehow connecting the pointer to the function pointer to a function with the original function that it points to. Okay, and then we run double bt is equal to and here we just pass pfun, and steps will be say 100 or say 50. Initial value of the account will be $100. The account is for 5 years and the risk-free rate is 0.05. Okay, and let's see what happens, if it works or not. So we step into the function. What is h? 0.01, 0.1. And let's see what this guy holds. So it holds the initial value of the money market account, then it always calculates the derivative and adds it to the previous state of the account. Okay, and when it ends, it returns some value, and this is the approximated value of the money market account after 5 years. we can compare it to the empirical result, because we can quite easily solve this equation, and you can indeed verify that the solution is bt is equal to b0 times exponential to rt. So if we use this equation here and we set up b0 is, say, 100, t is 5, r is 0.05, then our bt will be 100 times exponential to 5 times 0.05. And you can see that this number, which is the correct number, the perfect number, is quite close to what we have here as the approximated value. Okay, so you can see this one is definitely not perfect, but it's quite close. And if we increase the number of steps, so we would be using, instead of 50, say 1000, it would get even closer. Okay, so you can see we are quite close to the original result, but it's not exactly the one, and it's just because of the errors that are created during the approximation. Okay, so there is some cumulation of errors during the computation, because you can see here is some error and here it grows even more, and so on and so on. So there is some cumulation factor working in this algorithm. Okay, so this is quite undesired, and this can be reduced by using more sophisticated methods. So in my next video you will see how to use so-called Runge-Kutta method, which is of the fourth kind, which is much more efficient and accurate to evaluate the ODE. So thank you for watching my video.